Okay, great. All right. So this should be it. So yeah, as I was saying, work that I did together with Tanko and with Anton Akhmerov, who is the one of the PIs in our group. So I want to start by giving you just a rough agenda of what I'm going to talk about. I'll start by recapping some basic concepts about Majorana bound states. And I realize that some of you in the audience are already familiar with this, so I promise not to take too much time, but I want to be able to just emphasize a few concepts that are important for the rest of the presentation. After that, I'll go into how the algorithm we've developed actually works, and I'll show you some results and sanity checks that show that the algorithm is working as expected. All right, so as I said, let me start by giving you a little bit of an overview about Majoranas. So what are Majoranas? They are zero energy states that have non-abelian statistics. And that means that when you exchange them, you actually perform a unitary rotation in the state of the system. So with regular fermions, when you exchange two of them, you just multiply the wave function by -1. But with Majoranas, you actually have a degenerate subspace, and when you exchange them, you actually perform a rotation in this subspace. So in addition to these exotic exchange statistics, they are also topologically protected, meaning that you can use them to store and manipulate quantum information in a fault-tolerant way. That is connected to the fact that these Majorana modes are spatially separated so that you can basically encode information in non-local degrees of freedom that are immune to local perturbations to a certain extent, as we'll see. So these two features are why people are excited about Majorana modes. It's because they have these non-abelian statistics and because they are essentially hardware native error-corrected qubits. And that's why there's such a large experimental effort to try to realize them. Now, there are many possible ways of realizing them, or I should say many theoretical proposals on how to realize them, but by far the one that has received most attention relies on a few ingredients of solid-state physics, namely, you need a semiconductor that has spin-orbit coupling, you need superconductivity, and you need a strong magnetic field. Or in general, you could have some other way of breaking time reversal symmetry, but the most common approach to doing this is to apply a magnetic field. As we'll see, there are several ways of combining these ingredients together, but the most common one is the one that I'm showing on the right. So the one that has most experiments done on is this platform on the right, which is a quasi-one-dimensional nanowire, a semiconducting nanowire with spin-orbit coupling. And then, let me turn on the laser pointer. There's typically like an aluminum sheet attached to it that induces superconductivity in the wire, and also some electrostatic gates next to the device that allow tuning the density of states, or I should say the electronic density, and other gates that allow tuning tunnel barriers and perform transport spectroscopy. So this is the most common architecture, but there's another popular one, which instead relies on Josephson junctions. And this proposal arose as sort of a way to solve a conundrum that occurs in the architecture that I just described, the nanowires. And the problem there is that, as I mentioned, we need a strong magnetic field to drive the system into a topological regime. But the problem is that when you apply a strong magnetic field, you also kill superconductivity. So you have these two ingredients that are at odds with each other, and this competition adds another challenge to realizing this device. So in 2016, two groups independently had the idea of using Josephson junctions, and basically to replace the nanowire by a semiconducting to the electron gas with spin-orbit coupling, and then you attach two superconducting terminals on top of it. And now you make this separation narrow such that you have essentially a quasi 1D system here, and you have the exact same ingredients, right? You have spin-orbit coupling, you have superconductivity, and you have a B field. But importantly, you have an additional degree of freedom, which is the phase across the superconductors. And it turns out that you can use this phase in order to drastically reduce the magnetic field that you need to drive a topological phase transition. In fact, if you tune the phase to pi, you can theoretically create a topological phase with arbitrarily small magnetic fields. That's shown in this plot here at the bottom right. This is a topological phase diagram of this system, where on the x-axis we have the Zeeman field, on the y-axis we have the superconducting phase difference, and you see that at a phase difference of pi, we go directly at arbitrarily small magnetic fields. We go directly onto a topological phase. So that's quite an interesting development. Now, if the interface between the superconductor and the semiconductor isn't perfect, and the contact isn't perfect, there's some reflection, and the diamonds get deformed into this smooth shape, and you need to apply a finite magnetic field. But still, this is quite this is quite an elegant solution to this conundrum. And as a bonus, because it's a 2D platform, it's in principle easier to fabricate and scale with standard lithographic techniques. So that's Majoranas and Josephson junctions. And now I want to circle back to something I mentioned in the beginning, namely this topological protection, the Majorana modes. So Majorana modes are realized in superconductors, and superconductors have something called particle-hole symmetry, which forces the spectrum of the system to be symmetric with respect to zero energy. In other words, if you have a level at some positive energy, you need to have a particle-hole symmetric partner at minus that energy. And so ideally, your Majorana system looks like this. You have some levels. Well, you have your Majoranas at zero energy, and then you have some energy, some eigenstates separated by a finite energy gap. Now, if you wanted to ruin this qubit to destroy the Majoranas, you could try to move them away from the Fermi level like this, right? You could try to engineer a perturbation that does this, but that doesn't actually, that isn't actually allowed, because particle symmetry forbids this transformation, right? You need to always have a symmetric spectrum with respect to E equals 0. So there's no perturbation that does this, assuming you're still respecting particle-hole symmetry. This is not actually allowed. So actually, the only way to remove the Majoranas is to first close the bulk gap to bring these levels to the Fermi level, and then Majoranas can disappear. So the conclusion is that Majoranas are protected from perturbations, and the larger the topological gap, the larger is that topological protection. The larger are the perturbations that the system can withstand. And so that means that if we want to engineer reliable topological qubits, ideally we want large topological gaps. So that's kind of the setup for what I'm going to talk about next. In that spirit, there was a work that came out in 2019 from people in our group, where they looked at the question of how to increase the topological gap in these topological Josephson junctions. And what they found out is that if you take a straight Josephson junction and you make it zigzag shaped, you actually increase the topological gap by an order of magnitude. The reason for that can be seen from semi-classics. The idea is that if you have a straight junction, then you allow, then you have electron trajectories where electrons just propagate in the normal region without ever coming into contact with the superconductors. And so these long trajectories will result in low-lying states and small gaps. So the idea that Tom had was, why don't we just modify the geometry in order to kill off these trajectories, and hopefully that increases the gap. So he just made the junction zigzag shaped, and he was right. The gap increases by an order of magnitude. That's reflected in the wave functions, Majorana wave functions that I'm showing you on the right. So these are identical systems, identical Hamiltonian parameters, except that the one on the bottom has a zigzag shape. And you see that the Majorana wave functions in the zigzag junction are much less hybridized, and the gap is much higher. So this is a very nice insight, but it left open one question, which is, how do we find the optimal geometry? I mean, there's no a priori reason why zigzag should be the best. Clearly it works well, but there could be a better geometry. And we'd also like to find this optimal geometry in an algorithmic way, meaning we'd like to have a procedure that, given junction parameters, can find the optimal geometry for those parameters. So this is the main question that we try to address in this work. And now I'm going to introduce the algorithm that we came up with to try to tackle this problem. So the algorithm is composed of 4 main steps. First, we discretize the junction. So we work in a tight binding with a tight binding model. We use Quant, which is a package developed in our group, in order to create the model and manipulate it. Once we've created the model, we find a list of possible perturbations to the geometry of the junction. And we do that by first computing all the sites that are next to the boundary between the superconductor and the normal region. And then we consider perturbations where we just add or remove superconductivity from the boundary. So this is a perturbation where we are adding a superconducting site, and here we're removing the superconducting site. The motivation for considering sites next to the boundary is to try to promote a continuous evolution of the shape. So we don't want to add sites or remove sites at random. We want to hopefully steer the system into creating smooth shapes. So once we've created that list of perturbations, we compute the gap for each of them. We just diagonalize the system and see what the gaps are. And then we just choose the best perturbation, modify the system, and get back to the second step. This is the main idea of the work. There are 2 features that I want to highlight here, namely that the most computationally expensive step is by far to compute the gaps for each perturbation. But the good news is that this is completely parallelizable, meaning that each perturbation is independent, so we can just compute the gaps in parallel. So this can be done efficiently. And secondly, at each step, we're choosing the best possible perturbation. So this is known as a greedy step. So this is a term from computer science for algorithms where at each point you're making the locally optimal decision. So that's why this algorithm is greedy. So we went ahead and implemented this, and it worked, but it had a few problems still. So now I'm going to show you what those problems were and introduce modifications to the algorithm that solve these problems, and basically with these modifications we get the final algorithm that we show in the paper. So the first problem is just that the algorithm was quite slow, and that's because we were doing sparse diagonalization for each perturbation. We were doing, or another way of saying it was, we were doing exact diagonalization for each perturbation, and that's just very expensive. We're talking about a system that has maybe on the order of Hamiltonians are the order of 20,000 by 20,000, something along those numbers. So doing all these diagonalizations is quite expensive. Fortunately, there's an easy solution, which is just to use perturbation theory. So at each step, we're only adding 1 or 2 sites. That means that the norm of the perturbation is small, and so actually first order perturbation theory works quite well here. And this speeds up the algorithm by orders of magnitude. So that's nice. The second problem was that because it's a greedy strategy, we get stuck in local maxima, meaning that as soon as the algorithm finds a local maximum in geometry space, it's unable to escape it because you're always picking the optimal choice, right? So you always go back to the maximum. And to solve this, we need to introduce some sort of stochasticity into the optimization, kind of heating or something like that. The way we solve it is by introducing the fluctuations in the Hamiltonian. So at each optimization step, we introduce a small fluctuation to the magnetic field and to the chemical potential. And this allows the optimizer to circumvent these local maxima. The other reason for adding these fluctuations is that actually, we want to find a geometry that's hopefully optimal for a range of parameters and that's not overfit to a specific set of Hamiltonian parameters. So this also ensures that we do that we find a geometry that's good for a broad range of parameters. And now let me now show you results for a run with and without the parameter variation. So in the blue curve, I'm showing you the gap as a function of optimization step. And you see that it increases nicely until about 120 steps, where it just completely flatlines. It gets stuck. And in the red curve, I'm showing you the exact same simulation. So starting still from a straight junction and then letting the algorithm run, but with parameter variation. And I mean, we immediately see that the curve oscillates more. That's because we are, again, changing these parameters. But most importantly, it goes above the maximum value of the blue curve, right? It escapes this local maximum and still converges, but converges to a higher value. So that's nice. The insets show the shapes that we obtain for each run. And you also see that the red shape, or rather the shape for the red curve with parameter variation is much more reasonable, right? It doesn't have these kind of crazy variations. So that's also a nice byproduct of this parameter oscillation. Now, the third problem is that if you look at the output shapes, they are still a little bit irregular. I just said that this shape is better, but actually, if you look quite closely, there's still some kind of irregular features, things varying on the scale of the lattice constant. And we don't want that. We want shapes that are smooth and easy to fabricate. And so the way we tackle this is by using image processing techniques. Specifically, we apply image filtering. So this is just a standard operation in image processing, where at each pixel of an image, well, in our case specifically, at each pixel, we look at the pixels around it in a window of some size, and we assign to that pixel the median value in that window. And so this removes these fluctuations on the lattice, on the size of the lattice, on the scale of the lattice constant. And I'm showing you two examples where on the top plot, I'm showing you a shape obtained by the algorithm without filtering, and then I filter it, and indeed you see that the resulting shape is much smoother. So what we do is just every few steps, we apply this filter, and that constrains the algorithm to explore geometries that are smooth. So here are results for running the algorithm with and without the filtering. And you see that from top to bottom, when you compare the two pictures, the bottom shape is smoother and doesn't have these like islands of normal region, and the resulting gap is quite close. So finally, I want to just show a big plot that summarizes the results of this optimization. So again, starting from a straight junction and letting the algorithm evolve. So in the top plot here, I'm showing the gap at several points in phase space. So it's each orange curve corresponds to the gap at a particular value of chemical potential and magnetic field. And the blue curve corresponds to the average of the orange curves. What we see is that the average goes up smoothly, which is nice, but also each individual orange curve is increasing, which is what we wanted, right? We wanted a shape that where the gap was high for a range of parameters and not just for a specific point in parameter space. Then in the bottom two rows, I show the shapes as well as the Majorana wave functions for 3 different iterations that I mark here with vertical lines. We start from a straight junction, then somewhere in between, and this is the final shape. And you see that the Majorana wave functions get much more localized. In the bottom row, I show the phase diagrams for each shape. And you see that the overall gap is much higher by the end of the optimization. So once we collected these results, we were quite happy, but we had 2 remaining questions. Namely, is it the case that the algorithm is converging to a narrow local maximum? Like, are we finding a global maximum, which is what we want, or are we just, even with these strategies, maybe we're still getting stuck in some local maximum? And second, is the algorithm always producing the same shape, or can it produce different shapes depending on the physical situation that we input? So to address the first question, we basically, what we do is introduce modifications to the algorithm, and then we verify if we still get the same result. So we cannot prove that we're converging to a global maximum because the space is too large. But if we run the optimization in different ways and we still converge to the same shape, then it's more likely that we're finding a global maximum, or that at least we're finding a good maximum. And so we introduce 4 variations in the simulation, and we find that they all converge to the same shape. So first, we change the random seed. In another simulation, we allow the system to be mirror asymmetric. So previously, I was always adding 2 sites at a time at plus x and minus x to force mirror symmetry. Here, we allow the optimizer to add 1 site at a time, such that it can choose to find a mirror asymmetric geometry if it works well. You do another simulation starting from a zigzag geometry instead of starting from a straight junction. And we do another simulation where we add on-site disorder. So this is just to simulate a finite mean-free path. We do a standard procedure where we just add a random potential at each point, random on-site potential. And so I'm plotting here the difference of the reference shape with the shape we obtained in each of these simulations. So white here means that the shape at that point is identical. And if it's blue or red, it means there's a difference. And you see that essentially, and before that, so on the left is the difference halfway through the simulation. On the right is the difference at the end after convergence. And essentially, you see that these right pictures are very white, meaning that there's a very small difference between the reference shape and the shapes we obtain in these simulations. So essentially, even when we modify these starting conditions, we find the same shape, which suggests that the optimizer is indeed converging to a global maximum. And then finally, we introduce variation in the physical scenario that we're optimizing to see if we can get a different shape. And in particular, what we do is we introduce a chemical potential mismatch between the normal region and the superconducting region. And that's to simulate a finite work difference between superconductor and normal regions. And we first run the optimization in that scenario without a filter. And here it's quite interesting. The optimizer converges to a completely disordered shape. So, if you remember, if you look on the left, you had this run also without the median filter, but with matching chemical potential. And we see that, okay, the shape is not completely smooth, but it's smooth-ish, right? Whereas here on the right, it's really completely disordered. This is quite interesting. In this scenario, a disordered shape yields a high gap, and that the optimizer chooses to go for that. Once we add back the filter, we restore the smoothness of the shape. But interestingly, unlike the previous results, this one doesn't close all trajectories. So that's an interesting result. Also, if you look at the gap values, you see that they are lower than in the homogeneous chemical potential case. And we think that that's because when you introduce a mismatch, you allow for normal scattering to occur at the interface. And this, in principle, complicates the optimization problem. So it's harder to find high gap geometries. So that leads me to the end of the talk. I want to just summarize and give a few take-home messages. So we introduced a greedy strategy to find Majorana junction geometries that have high gaps. Our algorithm that we propose to do this is efficient because it relies on perturbation theory, and the main computational step is embarrassingly parallel. And finally, we looked at the robustness of the results with respect to changes in the starting point, presence of disorder, and we find that the results are robust with respect to that. In terms of open questions, there's still plenty that we could do. Perhaps the most kind of thing that jumps to mind immediately is whether this is immediately applicable to experiments or not. And at the moment, not quite, because we neglect a lot of effects in our simulations. So we don't consider electrostatics or magnetic field distribution, things like that. At the same time, the experimental knowledge that we have of these material platforms is still limited. So from our perspective, it doesn't make much sense to do these very detailed simulations without more knowledge about material parameters and things like that. And then finally, we would like to apply this algorithm to other systems. Still in the Majorana junction case, there's another proposal that involves Josephson junctions, where instead of using a magnetic field, you use supercurrents to break time reversal symmetry. And so you get rid of the magnetic field altogether. The problem with these proposals is that typically they have small gaps in the high density regime. So we're wondering if we can fix that by modulating the geometry with this algorithm. And then secondly, just more broadly, it would be interesting to find other inverse design problems in mesoscopic physics. The algorithm is quite general, I would say, as long as the problem can be mapped onto a tight binding model, we should be able to adapt it to other problems. And that's the end. So I want to thank you again for coming to the talk, and I'd be happy to take any questions you might have now.